Picture two cities. Both sit at the same latitude. Both receive the same amount of sunlight over the course of a day, and yet one of them heats up noticeably more than the other. The difference isn't in the soil, the wind, or the elevation. The difference is the clouds. Clouds that pass over each city for just a few hours a day. Why do satellites, year after year, keep detecting changes in cloud cover in exactly the places climatologists least expect? Why can the very same clouds, photographed from orbit, simultaneously cool the planet's surface and trap heat in the atmosphere? And why are clouds, not carbon dioxide, not methane, not melting glaciers, considered the single largest uncertainty in modern climate science? This isn't a film about rain. It isn't a film about weather. And it isn't another retelling of global warming. This is a scientific investigation into the most familiar and at the same time most mysterious object in the sky, the cloud. Every day, billions of people look up at the clouds without giving them a second thought. But for climatologists, clouds are one of the most complex systems that exist anywhere in Earth's atmosphere. The world's largest supercomputers, the most advanced climate models, dozens of satellites in orbit, and clouds still remain the one variable capable of throwing off even the most sophisticated forecasts. Picture a cloud field stretching for thousands of miles over the ocean, visible from orbit as a single, unbroken sheet. From the deck of a research ship below, it looks like an endless gray haze. From inside a research aircraft flying straight through it, that same field turns out to be an intricate three-dimensional structure. Droplets of every size, rising and sinking currents, layers of different density shifting within just a few hundred feet of altitude. Three completely different views of the same object, and not one of them tells the whole story on its own. At first glance, clouds would seem to be one of the best understood phenomena in atmospheric science. Humanity has been watching the sky for thousands of years. Meteorologists were already classifying clouds back in the early 19th century, sorting them into the categories we all recognize today: cumulus, stratus, cirrus, and nimbus. After 2 centuries of systematic observation, it would seem clouds should have given up their secrets long ago. But the more precise our instruments become, the clearer it is how shallow that confidence really was. Classifying clouds by appearance tells us almost nothing about what's happening inside them, at the level of individual droplets, ice crystals, and the microscopic particles around which this entire airborne architecture takes shape. And it turns out those microscopic processes govern the planet's global climate far more powerfully than anyone expected. To understand why, we need to go back to the most basic question of all. What do clouds actually do with the energy Earth receives from the sun? Every second, our planet receives an enormous amount of solar radiation. Part of that energy is absorbed by the surface, warming the oceans, the land, the air. Part of it is reflected straight back into space. And clouds are one of the main regulators of exactly how much of that energy stays on the planet and how much escapes back out into the universe. Here's where the first paradox hides. Clouds cool the Earth and warm it at the same time, not by alternating between the two, but literally simultaneously, depending on the type of cloud, its altitude, its thickness, and the time of day. Bright, dense clouds sitting low in the sky act like enormous mirrors. They reflect a significant portion of sunlight straight back into space, keeping that energy from ever reaching the ground or the ocean. That's the cooling effect, the reason cloudy days feel cooler than clear ones. But high, thin, translucent clouds work differently. They let sunlight pass through to the surface below, while trapping the infrared radiation trying to escape back into space after sunset. It works like a blanket. It doesn't stop heat from coming in, but it does stop heat from leaving. That's the warming effect. So the very same category of object, clouds, can push in 2 opposite directions at once. And which effect wins out in any given region of the planet depends on an incredibly delicate balance of physical parameters. To dig even deeper into this paradox, we need to drop down to the level of physics itself, to the place where a cloud is actually born. A cloud begins with an invisible process. Warm, moist air rises, and as it climbs, the pressure around it drops, causing the air to expand and cool. This is called adiabatic cooling. At some point, the air cools enough to become saturated with water vapor, meaning it can no longer hold all of its moisture as a gas. But for that vapor to turn into a liquid droplet, it almost always needs something to hold on to, a tiny particle around which condensation can begin. This is where cloud condensation nuclei enter the story. Microscopic particles of dust, sea salt, soot, or sulfur compounds floating through the atmosphere in staggering numbers. Every droplet in a future cloud is born around one of these particles. And exactly how many particles are available in a given volume of air determines that cloud's fate far more than you might expect. If there are few particles, water vapor condenses around a small number of nuclei, forming relatively few large droplets. A cloud like that looks less dense and lets more sunlight through. But if there are many particles, in air polluted by industrial emissions or ship exhaust, for example, that same volume of water vapor gets spread across a much larger number of nuclei, forming many small droplets instead. A cloud made of many small droplets reflects significantly more sunlight than a cloud with the same amount of water made of just a few large ones. In atmospheric science, this is known as the first indirect aerosol effect, sometimes called the cloud brightening effect. It's exactly why ship tracks show up so vividly in satellite images, not because those clouds contain more water, but because the same amount of water has been divided among far more droplets. But there's a second, equally important effect. Clouds with more small droplets tend to take longer to turn into rain. Large droplets fall as precipitation much faster than small ones. That means more polluted clouds can persist longer, cover a larger area, and keep reflecting sunlight for longer before they finally dissipate. This is known as the aerosol effect on cloud lifetime. Together, these two effects, the change in reflectivity and the change in how long a cloud survives, make up what climatologists call the aerosol indirect effect on climate. And because these effects are so difficult to quantify precisely, the overall cooling influence of industrial aerosols on the planet's climate remains one of the least precisely known quantities in all of climate science, far less certain than, say, the direct radiative effect of carbon dioxide. Scientists call this duality cloud radiative forcing, and it's exactly why climate models diverge in their forecasts even when run under identical carbon dioxide emission scenarios. If clouds behaved predictably, climate science would have closed one of its biggest questions of the decade long ago. But clouds don't behave predictably. To understand the depth of this problem, we need to descend further, literally, into the lower layers of the atmosphere, to where the planet's most puzzling clouds take shape. Stretching across vast expanses of open ocean, far from any coastline, lie low cloud fields known as stratocumulus clouds. They look unremarkable, a solid gray blanket, like a sheet of cotton stretched across the water. But these clouds have turned out to be a genuine scientific headache for climatologists. Stratocumulus clouds blanket colossal areas of ocean, especially along the western coasts of continents, where cold ocean currents create ideal conditions for their formation. These clouds reflect an enormous amount of solar energy back into space. If they were to disappear or shrink significantly, it would drive a noticeable additional warming of the planet, without a single extra ton of carbon dioxide entering the atmosphere. And this raises a question that has troubled climatologists for years. What will happen to these clouds as the planet continues to warm? Some studies based on climate modeling point to an unsettling scenario. At a certain level of atmospheric carbon dioxide concentration, stratocumulus decks could break apart fairly abruptly, dissolving into scattered, disconnected cumulus clouds that reflect far less sunlight. And this could happen not gradually, but relatively quickly by geological standards, over the course of decades, not millennia. The mechanism behind this potential collapse comes down to a delicate balance within the cloud layer itself. Stratocumulus clouds exist thanks to constant cooling at the cloud top, the layer facing open sky. Heat escapes upward. The air at the top of the cloud cools, becomes heavier, and sinks back down through the cloud layer, driving a continuous circulation that keeps the cloud dense and uniform. But as carbon dioxide concentrations rise in the free atmosphere above the cloud, that cooling process weakens. The air above the cloud itself grows warmer and holds on to more of the outgoing radiation, capturing energy that used to escape straight into space. The internal circulation slows, the cloud layer becomes less stable, and it gradually begins to break apart into scattered clusters. Calculations from several independent research groups suggest that at sufficiently high atmospheric carbon dioxide concentrations, this kind of stratocumulus breakup could theoretically occur over a relatively short period by climatic standards, triggering an additional sharp rise in global temperature beyond what standard models predict when this mechanism isn't accounted for. It's worth stressing, this isn't an established fact, but one possible scenario based on simplified models of cloud dynamics. That's exactly why the scientific community treats such projections with caution, continuing to test them against more complex, more detailed models. It's also worth noting that abrupt, step-like shifts in the climate system are far from rare when you look at Earth's history on a broader timescale. Paleoclimate records drawn from ice cores, ocean sediment layers, and other natural archives show that the planet's climate has, in the past, sometimes changed not gradually, but in sudden jumps over relatively short spans of geological time. While it's difficult to reconstruct cloud processes directly from those archives, the indirect signs of abrupt shifts in past temperature and precipitation make climatologists take seriously the possibility of a similarly abrupt cloud response in the future, rather than dismissing it as a purely theoretical exercise. Other research suggests that this scenario depends heavily on fine details of cloud physics that current models describe with insufficient resolution. Shift a model's horizontal grid scale by just a few miles, and the outcome can change dramatically. That's exactly why stratocumulus clouds remain one of the central focuses of modern atmospheric science. This isn't some abstract detail. It's one of the key factors determining just how strongly the planet will respond to the continued rise in greenhouse gas concentrations. Observations from recent years have added another detail to this picture, one that's just as interesting as the breakup scenario itself. Satellite data show that the extent and density of stratocumulus clouds over certain ocean regions already display significant year-to-year variability, closely tied to the sea surface temperature in those same regions. The warmer the ocean beneath the cloud layer becomes, the less stable that layer turns out to be, a pattern consistent with theoretical predictions, though the precise quantitative match between observations and models remains an area of active research rather than a settled question. But stratocumulus clouds are only part of the puzzle. Cumulus clouds, those familiar puffy formations with a flat base and a rounded top, add their own layer of complexity. A single small cumulus cloud seems like a simple phenomenon. Warm air rises, cools, water vapor condenses, and a cloud forms. But once you're dealing with fields of thousands of these clouds, interacting with one another, redistributing moisture, energy, and turbulence across vast stretches of sky, the simplicity vanishes. The interaction between individual cumulus clouds is one of the hardest problems to calculate in all of atmospheric physics. precisely because these clouds are often smaller than the grid resolution used by most global climate models. Observations of cumulus fields over the tropical ocean have revealed another unexpected pattern. Clouds within these fields are far from randomly distributed. Sometimes they arrange themselves into clearly ordered structures, regular rows, rings, or honeycomb-like cellular patterns stretching for hundreds of miles. Researchers studying these ordered structures using high-resolution satellite imagery have found that the shift from a chaotic, random arrangement of cumulus clouds to an ordered one noticeably changes the overall reflectivity of the cloud field, even when the total amount of water contained in the clouds stays exactly the same. This discovery turned out to matter a great deal, because most current climate models simply aren't capable of reproducing this kind of self-organization in cloud fields. They don't have the spatial resolution needed to capture the difference between a chaotic and an ordered distribution of clouds, which means models can systematically misjudge the reflectivity of entire ocean regions simply because they can't see this subtle structural organization, one that's only visible in the high-resolution imagery. In other words, supercomputers capable of modeling the entire planet's climate decades into the future physically cannot directly calculate the behavior of a single cloud just a few hundred yards across. Instead, they rely on simplified mathematical approximations known as parameterizations. And a significant share of the uncertainty in today's climate forecasts is hiding inside those very approximations. To grasp the scale of this problem, it helps to look at actual numbers. A typical global climate model divides the planet's atmosphere into cells ranging from several dozen to 100 miles across. Everything that happens inside one of these cells, the birth of individual cumulus clouds, their growth, merging, breakup, and rainfall, isn't calculated directly by the model. Instead, it's described using an averaged formula, calibrated against observations and more detailed local studies. That averaged formula is known as convective parameterization. It works reasonably well for describing broad trends, but it struggles with rare, high-impact events, a sudden burst of intense thunderstorm activity, for instance, which can drastically alter the local energy balance within just a few hours. That's exactly why different research centers, each building their own version of a climate model, end up with noticeably different results, even when starting from the same underlying physical laws and the same greenhouse gas input data. In recent years, climatologists have gained a fundamentally new tool for tackling this problem, so-called global convection permitting modeling, in which the size of each computational cell shrinks down to just a few miles, and in some experimental projects, down to just a few hundred yards. This demands computing power that would have seemed like science fiction not long ago. Calculations like these run on the world's largest supercomputer systems and consume staggering amounts of energy for every minute of simulated climate. But the payoff is real. High-resolution models are already producing noticeably more realistic cloud field structures than their coarser grid predecessors. There's a third type of cloud that adds yet another layer of complexity: cirrus clouds. These thin, translucent, wispy formations sit very high up, right at the edge of the troposphere, where temperatures drop to -50 degrees Fahrenheit and below. Cirrus clouds aren't made of water droplets at all. They're made of tiny ice crystals. Cirrus clouds, as a rule, tend to warm the planet rather than cool it. They barely reflect any sunlight. They're simply too thin and transparent for that. But they're remarkably effective at trapping outgoing heat radiation from the Earth below. And here's something particularly interesting. Cirrus clouds sometimes form artificially, as a result of air travel, when a jet's condensation trail at high altitude turns into a lasting cirrus cloud that can persist for hours. Another peculiarity of cirrus clouds has to do with the very mechanism by which ice crystals form in the upper atmosphere. Unlike water droplets, which usually only need a small amount of supercooling before they begin condensing around a nucleus, ice crystals often require far deeper supercooling. Water can remain liquid in a supercooled state at temperatures well below freezing, down to nearly -40 degrees Fahrenheit, before it spontaneously freezes without the help of a specialized ice nucleus. This phenomenon is called supercooling, and it explains why liquid droplets and ice crystals can coexist at certain altitudes, competing for the very same water vapor. It's precisely this competition between the liquid and solid phases of water that makes the upper layers of clouds so sensitive to the smallest changes in temperature and the concentration of ice nucleating particles in the atmosphere. A tiny amount of dust, carried by the wind from a desert on another continent entirely, can serve as that one missing nucleus around which mass crystallization of supercooled water begins, changing the optical properties of an entire cloud system within minutes. There's yet another category of clouds, born directly from human activity rather than natural processes: aircraft condensation trails, which many of us have seen streaking across the sky behind high-flying airliners. At high altitude, where air temperature drops well below freezing, water vapor from jet exhaust condenses instantly around soot particles, forming a thin white streak. In dry air, that trail vanishes quickly, but in humid, supersaturated air at cruising altitude, that same trail can not only persist, but spread, turning into an extended cirrus cloud that sometimes lingers in the sky for hours after the aircraft itself is long gone. Scientists studying aviation's climate impact have found that these induced cirrus clouds can contribute to the planet's global radiative balance by an amount comparable to, and possibly even exceeding, the direct carbon dioxide emissions from aviation itself. That's a fairly surprising result. It isn't so much the fuel burned that matters most, but the indirect effect through changing cloud cover, which turns out to be one of the aviation industry's biggest climate footprints. That's exactly why, in recent years, experimental proposals have emerged to slightly adjust the cruising altitude of individual flights, steering them away from the layers of atmosphere most prone to forming persistent contrails. Early trials have shown promising results, but scaling measures like these up to the entire global aviation industry remains a difficult engineering, economic, and scientific challenge. Part of the difficulty is that predicting, ahead of time, exactly which layer of the atmosphere will be humid enough to sustain a persistent trail isn't simple. These zones are narrow, constantly shifting, and poorly captured by the standard weather models used for flight planning. On top of that, avoiding one of these zones by climbing or descending a few hundred feet inevitably changes fuel consumption, which means the trade-off has to be weighed carefully. The benefit of reducing induced cloud cover has to outweigh the cost of the extra direct carbon dioxide emitted by a less efficient cruising altitude. This brings us to a subject climate science has been talking about, especially loudly in recent years: the role of aerosols and human influence on clouds. And not just through carbon dioxide. Clouds don't form out of nothing. Every water droplet in a cloud needs a tiny particle to condense around. It could be a speck of dust, sea salt, soot, or a sulfur compound. These particles are called cloud condensation nuclei. The more of these nuclei are present in the air, the more small droplets form, and the denser and more reflective the resulting cloud becomes. That means human activity can directly influence the optical properties of clouds, entirely independent of greenhouse gases. A similar, though far larger-scale natural source of aerosols is volcanic eruptions. Major eruptions inject colossal volumes of sulfur compounds into the stratosphere, which oxidize into microscopic sulfuric acid aerosols capable of lingering in the upper atmosphere for months or even years. gradually spreading across the entire planet on high-altitude winds. These volcanic aerosols don't form clouds directly, but they noticeably increase the reflectivity of the entire atmosphere, producing a measurable cooling of the planet's surface for a year or two following a major eruption. Observations of the aftermath of major 20th century volcanic eruptions gave climatologists one of the most convincing natural tests of theoretical models of aerosol climate impact. By comparing the cooling predicted by models against the temperature drop actually recorded by satellites and ground stations, scientists were able to calibrate their models' sensitivity to aerosol forcing, a rare opportunity when nature itself ran a massive, if unplanned, experiment on the entire planet. One of the clearest examples of this kind of influence turned out to be shipping. Ship exhaust contains sulfur compounds that become condensation nuclei over the ocean. Satellites have repeatedly captured distinctive bright cloud streaks trailing along major maritime shipping routes, known as ship tracks. These streaks are clearly visible from space precisely because the clouds along a ship's path reflect noticeably more sunlight than the surrounding cloud field. And here comes a genuinely unexpected twist in this story. In the year 2020, new international regulations took effect, sharply limiting the sulfur content allowed in marine fuel, aimed at reducing air pollution and protecting human health. That measure was the right call for air quality, but it came with an unexpected side effect on climate. Cutting sulfur emissions meant fewer condensation nuclei over the ocean, and therefore less dense, less reflective clouds along shipping lanes. Some researchers have linked this shift to an acceleration of warming observed in certain regions of the Atlantic Ocean in the years that followed. This became one of the most widely discussed examples of just how subtly and how invisibly human activity can alter the planet's radiative balance through clouds, not only through greenhouse gases. The ship track story gave rise to another idea that's actively debated in the scientific community today: the possibility of deliberately brightening marine clouds. The concept is simple and also deeply controversial. If spraying microscopic sea salt particles over a section of ocean can make clouds more reflective, then in theory, that method could be used intentionally to offset part of global warming. This concept is known as marine cloud brightening, and it belongs to the broader category of ideas known as climate geoengineering. Proponents of such experiments point out that this kind of intervention could, in theory, produce a fast cooling effect in specific regions, for instance, to protect vulnerable coral reefs from overheating. However, the overwhelming majority of climatologists emphasize that the long-term consequences of intervening in cloud systems this way are still poorly understood, and that the very idea of deliberately managing clouds raises serious ethical and geopolitical questions, not just scientific ones. For now, this remains the domain of small, controlled experiments and theoretical calculations, not a practice applied at industrial scale. This discovery pushed climatologists to look at the problem more broadly. If an accidental, unintended change in atmospheric composition could so noticeably affect cloud cover across an entire ocean region, just how large is the role of aerosols in the overall picture of climate change over recent decades? Scientists are trying to answer that question using one of the most ambitious fields in modern Earth science: satellite observation of the atmosphere. Since the mid-20th century, humanity has launched dozens of satellites specifically dedicated to studying clouds and the planet's energy balance. One of the most important projects is the CERES mission, which provides long-term measurements of exactly how much energy Earth receives from the Sun and how much it radiates back into space. It's CERES data that allows scientists to directly track the planet's global energy imbalance, the difference between incoming and outgoing energy, which ultimately determines whether the planet is warming or cooling. The multi-decade CERES data record has produced a finding that's become one of the most widely discussed in climate science over the past decade. the planet's global energy imbalance hasn't stayed constant. It's been growing noticeably year after year, and the pace of that increase has turned out to be faster than most previous generation climate models predicted. Researchers attribute part of that acceleration directly to changes in cloud cover, specifically to a shrinking area of bright, sunlight-reflecting low clouds over certain ocean regions. This observation has become one of the most direct pieces of evidence to date that clouds don't just passively respond to warming, they actively help determine its pace. Another critical instrument is the MODIS spectroradiometer, mounted on the Terra and Aqua satellites, which photographs nearly the entire surface of the planet every single day, tracking cloud cover, cloud top temperature, optical thickness, and a wide range of other parameters. Before the satellite era began, scientists could only rely on scattered ground-based observations, weather stations, weather balloons, and the occasional measurement from research aircraft. That kind of data offered only a fragmented picture, limited to specific points on the map and specific moments in time. The arrival of satellites in the late 20th century was a genuine revolution. For the first time in history, humanity could observe the cloud cover of the entire planet simultaneously, consistently, year after year. That continuous, decades-long data archive turned out to be priceless. A single snapshot of clouds tells you very little about climate, but decades of consistent observation reveal statistically meaningful trends. How average cloud height is changing, how reflectivity is shifting, how the geographic distribution of different cloud types is evolving. These long-term data records have become the foundation on which the entire modern science of clouds and climate is built. The CloudSat and CALIPSO missions hold a special place in this story. Unlike ordinary satellite imagery, which only shows clouds from above, these two satellites, flying in near-perfect synchrony with each other, used radar and LiDAR to literally see straight through clouds, creating vertical slices of the atmosphere. Thanks to this data, scientists got their first detailed three-dimensional picture of the internal structure of cloud systems across the entire planet, the distribution of droplets, ice crystals, and layers of varying density within a single cloud mass. The European Copernicus program added its own network of Sentinel satellites to this picture, significantly expanding the coverage and precision of observations of the atmosphere, ocean, and land. Together with data from NASA and NOAA, these observations form one of the most complete atmospheric data archives ever assembled by humanity. Also worth noting is the international network of geostationary weather satellites, which hover continuously over the same point on the equator at an altitude of tens of thousands of miles. Unlike polar orbiting satellites, which pass over any given point only a few times a day, geostationary satellites can watch the development of individual storm systems, tropical cyclones, and frontal cloud bands minute by minute around the clock. It's thanks to geostationary satellites that forecasters around the world get something close to a real-time video feed of cloud cover, an indispensable tool for early warning of dangerous weather. Ground-based observations haven't lost their value in the satellite era either. Networks of ground radar continue to track the internal structure of precipitation with a level of detail even the most advanced orbital instruments can't match, while networks of surface stations measure cloud base height using laser instruments known as ceilometers. Combining ground-based, airborne, and satellite data remains the gold standard of modern cloud research. No single data source tells the whole story on its own. And yet, despite this enormous volume of observations, different global climate models still produce noticeably different forecasts for exactly how clouds will respond to continued warming. This uncertainty is significant enough that it's considered one of the main reasons the projected range of temperature rise under a doubling of atmospheric carbon dioxide remains fairly wide, rather than converging on a single precise number. To understand why even today's most advanced satellites and supercomputers still can't fully resolve this uncertainty, we need to turn to another factor: the ocean's influence on cloud formation. The ocean covers more than 70% of the planet's surface, and a significant share of global cloud cover forms directly above it. Sea surface temperature, the pattern of ocean currents, the rate of moisture evaporation, all of these directly determine where and what kind of clouds will form. One of the most powerful factors capable of temporarily reshaping cloud cover across entire ocean regions is El Niño, the periodic warming of surface waters in the central and eastern Pacific. During strong El Niño episodes, the pattern of cloud cover over the tropical Pacific shifts noticeably. Zones of intense thunderstorm activity move, which in turn affects global weather systems from monsoons in Asia to storm seasons across the Americas. The opposite phase of this pattern, La Niña, in which surface waters in the central and eastern Pacific turn colder than normal, triggers changes in global cloud cover that are nearly a mirror image, though not identical. Zones of intense rising air and the powerful thunderstorm activity that goes with them shift in the opposite direction, which also reshapes monsoon systems, storm tracks, and rainfall patterns across huge stretches of territory, from Australia to South America. Together, these two opposing phases, collectively known as the El Niño Southern Oscillation, remain one of the most important natural sources of year-to-year variability in global temperature and cloud cover. It's the overlay of this natural variability on top of the long-term trend of human-driven warming that makes interpreting any single warm or cold year such a challenging task. Climatologists have to carefully separate the short-term swings driven by ocean cycles from the steady, long-term trend driven by the buildup of greenhouse gases in the atmosphere. El Niño serves as a kind of natural laboratory for climatologists. By watching how cloud cover and the planet's energy balance shift during strong episodes of Pacific Ocean warming, scientists get a rare opportunity to test just how accurately climate models can predict the real-time cloud response to changing ocean temperature, not just in theoretical scenarios. Changes in cloud cover play a critical role not only in the global energy balance, but also in the formation of extreme weather events: storms, hurricanes, intense downpours. Thunderstorm cloud systems forming over warm patches of ocean can grow into powerful tropical cyclones, whose energy is largely determined by how much heat and moisture has built up in the upper ocean, and how quickly that heat transfers into the atmosphere through condensation. That's exactly why modern research increasingly treats clouds not as an isolated, standalone element of the atmosphere, but as part of a single, interconnected ocean-atmosphere system, in which the smallest change to one parameter can trigger a chain reaction affecting the climate of entire regions of the planet. This connection shows up especially vividly in the process of rapid intensification in tropical cyclones, a phenomenon in which a storm strengthens from an ordinary tropical depression into a major top-category hurricane within just a matter of hours. For a long time, this remained one of the hardest aspects of hurricane season to forecast. Modern research shows that a key role is played by the interaction between the upper levels of a cyclone's cloud tower and the surrounding atmosphere. If dry air infiltrates a developing storm, it can suppress its growth by disrupting the cloud's internal structure. But if the surrounding atmosphere stays saturated with moisture, nothing stands in the way of the cloud tower growing almost unimpeded, accelerating the intensification process. Real-time satellite observation of cloud structure inside tropical cyclones has become one of the most important tools in modern meteorology. By analyzing the shape, height, and symmetry of the eye wall surrounding a storm's center, forecasters can predict with noticeably greater accuracy whether a cyclone will keep strengthening or start to weaken in the hours ahead. A forecast whose precision directly affects the evacuation of millions of people in coastal regions. A similar dynamic plays out in mesoscale convective systems, large clusters of thunderstorm clouds that can merge into a single structure hundreds of miles across and persist for many hours, bringing intense rainfall, damaging wind, and sometimes tornadoes. These systems tend to form especially often over broad plains, where warm, moist air on one side meets drier, cooler air masses on the other, creating ideal conditions for powerful vertical cloud development. A specific category of these systems, known as mesoscale convective complexes, can deliver a month's worth of rainfall for an entire region in a single night, triggering flash floods in areas thousands of miles from any ocean. Studying the internal structure of these systems using weather radar has shown that they often contain a kind of internal climate cycle of their own. Warm, moist air rises at the leading edge of the system, fueling intense thunderstorm activity, while precipitation falling behind it cools the air and creates its own downdraft, which in turn helps drive the entire system forward, letting it persist far longer than any single thunderstorm cloud within it ever could on its own. Just as fascinating is the role clouds play in shaping monsoon systems, on which the lives of hundreds of millions of people across South and Southeast Asia directly depend. A monsoon is a large-scale, seasonal circulation in which the difference in heating between land and ocean drives a steady flow of moist air from the sea onto the continent, forming broad bands of intense thunderstorm cloud cover that deliver the bulk of a region's annual rainfall within just a few months. The smallest shift in the timing of monsoon onset or in the intensity of the cloud cover that comes with it can directly affect crop yields for entire countries, which makes accurate monsoon cloud forecasting one of the most practically valuable tasks society has asked of this science. There's one more region of the planet where clouds behave strangely enough to deserve special attention in this investigation: the polar latitudes. Over the Arctic and Antarctic, clouds form under conditions radically different from those over the tropical ocean. Extremely low temperatures, long stretches of polar night or polar day, a highly reflective icy surface below, all of this creates a completely distinct dynamic. Polar clouds often consist of a mixture of supercooled water droplets and ice crystals at the same time, and that mixture can remain stable for far longer than classical cloud microphysics models would predict. These mixed-phase clouds have turned out to be a particularly tough challenge for climate modeling. Whether water droplets or ice crystals dominate within a cloud directly determines how much heat that cloud traps above the icy surface below, and that in turn affects the rate of sea ice and glacier melt, one of the most visible and most alarming indicators of climate change on the planet. Researchers working at polar stations and analyzing data collected by research aircraft have found that many global climate models systematically misjudge the ratio of ice to liquid water in polar clouds. This seemingly narrow technical detail has a surprisingly large effect on how quickly models predict warming in the Arctic, a region that, according to decades of observation, is warming faster than the planet as a whole. An additional layer of complexity in the Arctic comes from the reflectivity of the surface itself. Sea ice and snow reflect far more sunlight than open, dark ocean water. As ice melts, the exposed dark surface absorbs more solar energy, which accelerates further melting, a textbook example of what's known as the ice albedo feedback. But clouds interfere with this process too. More open water means more evaporation and potentially more low clouds, which can either amplify or partially offset local warming depending on the season and the angle of the sun at high latitudes. Untangling this chain of interlocking feedback loops is one of the most pressing challenges in polar climatology today. All of this naturally raises the question: what has actually been proven about clouds, and what remains an open scientific question? Before summing up, it's worth pausing on one more detail that rarely makes it into popular accounts of climate: the role clouds play in mountain and desert regions. Over high mountains, clouds form according to their own rules. Air forced upward along a slope cools far more quickly than it would over flat terrain, producing distinctive lens-shaped clouds and stable wave-like cloud structures that can hold their shape for hours, even as strong wind blows straight through them. These clouds have become an important indicator for researchers studying atmospheric turbulence and for aviation, since their shape directly reflects the structure of airflow around mountain ranges. Studying mountain clouds also has very practical value. The wave turbulence generated by air flowing over mountain ridges poses a real hazard to aviation, and the ability to recognize characteristic lens-shaped clouds as a visual sign of that turbulence remains an important skill for pilots and aviation forecasters to this day, despite all our modern forecasting systems. Desert regions, by contrast, interest climatologists precisely because of the absence of clouds. The extremely low humidity above the planet's largest deserts means that almost all incoming solar energy reaches the surface unimpeded, and at night, that same energy escapes back into space just as freely, which is why deserts experience such dramatic daily temperature swings. Studying how the rare clouds that do occasionally form over deserts, during infrequent rainy seasons, for instance, helps scientists better understand the threshold conditions needed for moisture to condense under conditions of extreme dryness. It's firmly established that clouds have a colossal effect on the planet's energy balance, comparable in scale to the greenhouse effect itself. It's firmly established that low clouds, on the whole, work to cool the planet, while high cirrus clouds work to warm it. It's firmly established that aerosols, including those of human origin, can alter the optical properties of clouds by changing the number and size of droplets within them. It's firmly established that satellite observations are recording real, measurable changes in global cloud cover over recent decades. It's also firmly established that global cloud cover makes up a significant share of the Earth's surface at any given moment, even though that share varies noticeably with season, latitude, and the phase of natural cycles like El Niño. It's firmly established that cloud distribution is highly uneven. Some regions of the planet, the equatorial zones of rising air for instance, stay heavily overcast for most of the year, while the subtropical zones of sinking air, home to the planet's largest deserts, remain mostly cloud-free. But one of the most fundamental questions remains open. How will the combined response of every type of cloud to global warming ultimately affect the planet's overall climate sensitivity? Will clouds amplify the warming driven by rising greenhouse gas concentrations, or will they partially offset it? And if they amplify it, by how much? This is precisely the question behind the concept of cloud feedback, which, by climatologists' own admission, remains one of the largest sources of uncertainty in all of climate science. Different models, using different methods to describe cloud microphysics, arrive at different answers, and the gap between those answers can shift the final climate forecast by several degrees, which is enormous in terms of its consequences for the planet. Scientists keep refining this picture using ever more sophisticated tools. New generations of climate models are attempting to directly calculate the behavior of individual clouds on very fine spatial grids, an approach known as convection resolving modeling. It demands tremendous computing power, but it's already helping to narrow some of the most serious discrepancies between models. At the same time, satellite technology keeps advancing. New missions carry more precise instruments, capable of measuring not just cloud amount and altitude, but the detailed size of droplets, ice content, and vertical structure at even finer resolution than before. Each new mission adds another layer of data to the overall picture, gradually narrowing the range of uncertainty without eliminating it entirely. Among these new projects, a next generation of missions stands out, taking over from the now retired CloudSat and CALIPSO. One of them is a satellite studying the interaction between clouds, aerosols, and the planet's energy balance with even greater precision than previous missions, combining radar, LiDAR, and a radiometer on a single platform so that data can be compared without timing mismatches between instruments. Another project focuses on detailed observation of ocean color and atmospheric aerosols and their interaction with clouds, directly tied to the shiptrack story and the role of sulfur compounds discussed earlier. These new missions were designed specifically to close the gaps described above, to more precisely measure the ratio of droplet size to droplet number within clouds, to more clearly separate the contribution of natural versus human-made aerosols, and to more accurately link atmospheric particle data to its direct effect on specific cloud systems. Every step forward in observational precision directly improves climate models' ability to reproduce the atmosphere's real behavior, and, in turn, the reliability of the forecasts that governments and international organizations around the world depend on. Alongside the advance of observation technology, there's also a large-scale, ongoing effort to compare the results of climate models developed by dozens of research centers worldwide. In these international model comparison programs, researchers deliberately run different models under identical starting conditions to understand exactly where and why their forecasts diverge. Time and again, cloud feedback turns out to be one of the leading sources of disagreement between models, far more significant than, say, differences in how they describe glacier melt or changes in vegetation cover. Field campaigns deserve special mention too. Large international expeditions in which research ships and aircraft spend weeks or months conducting intensive observations of a specific cloud region, collecting data that simply can't be gathered from space, direct measurements of droplet size inside clouds, the chemical composition of condensation nuclei, vertical profiles of temperature and humidity accurate to the meter. These campaigns, run jointly by scientists from multiple countries, are regularly organized over the regions with the largest stratocumulus fields on the planet, off the western coasts of South America and Africa, precisely because these clouds remain the least understood and most climatically significant category of low cloud cover on Earth. None of this means climate science has stood still. On the contrary, in recent years, the range of cloud-related uncertainty has narrowed noticeably, thanks to the combined analysis of satellite observations, laboratory experiments in cloud microphysics, and increasingly detailed modeling. But eliminating that uncertainty entirely hasn't been possible so far, and it's unlikely to happen anytime soon. There are simply too many physical processes happening simultaneously, at scales ranging from fractions of a millimeter to thousands of miles. And maybe that's the central lesson of this whole story about clouds. We're used to thinking of climate science as, first and foremost, the science of carbon dioxide, of temperature records, of melting glaciers. But one of the most fundamental mysteries in modern climatology isn't hiding somewhere in the distant polar regions. It's right above our heads, in clouds that every person has seen thousands of times in their life, almost never stopping to consider just how complex their nature really is. It's worth remembering how this investigation began. Two equally sunny cities receiving different amounts of heat because of a few hours of cloud cover separating one from the other. Behind that simple observation lies all the complexity we've walked through step by step. From a single droplet condensing around a microscopic grain of salt somewhere over the ocean, to global supercomputer models trying to predict the planet's climate a century into the future. Every level of this story, from microphysics to the planetary energy balance, turned out to be connected to the level next to it by invisible but critically important threads. Clouds don't just decorate the sky. They protect the planet from excess solar heat while trapping outgoing heat radiation, all at the same time. They respond to ocean temperature, to atmospheric composition, to human activity, sometimes in the most unexpected ways, as in the story of sulfur emissions from ships. And they remain insufficiently understood, even with dozens of satellites watching the planet around the clock, and the most powerful supercomputers humanity has ever built. The more satellite technology and climate modeling advance, the better scientists understand the role clouds play in the planet's climate system. But many of the key questions, just how strongly clouds will amplify future warming, whether specific cloud types will hold up as temperatures continue to rise, exactly how their distribution over oceans and continents will change, still call for further research. And maybe that's exactly why clouds deserve the same perspective this story opened with. Not one of fear, but of genuine wonder at the complexity hidden inside the most ordinary sight in the sky. One that turned out to be one of the greatest scientific mysteries about our planet. Next time you look up and see an ordinary cloud drifting overhead, it's worth remembering, somewhere inside that seemingly simple shape, an extraordinarily complex interplay is unfolding. Droplets, ice crystals, microscopic particles, and streams of energy, all interacting in ways that the planet's best minds, armed with the most powerful computers and the most precise satellites ever built, are still working to understand. Step by step, closing in on one of the most beautiful and most stubborn mysteries of Earth's atmosphere.